Yes, let's start chapter number 4 today. So you can see my YouTube channel, subscribe it and press the bell button so that when I upload new videos, so you will be notified for. Chapter number 4 is the laws of motion. So in this chapter we'll be discussing the dynamics. So means the motion, we study the motion of the objects when we see what happens when different forces are acting on them. So accordingly we have 3 laws of motion given by Newton. First of all, as I told you, that dynamics is the study of the forces that cause objects and systems to move. We have 2 types of forces. Number 1, the contact forces, and number 2, the field forces. Contact forces mean once you are applying the force on some objects, you touch that surface. That object is in contact with you, so we call them contact forces. Like if you are pulling this spring or pushing it, this is a type of force, we call it contact force. This one again, the second case, you are pulling it, the kid's cart, and again this is contact force. Once you are kicking a football, your foot is in contact with the ball once you are kicking it. Some forces are, forces at a distance. No need to have direct contact with the object or with the other body. See, like you see, there is a force of attraction between any 2 objects. This one, small object, is a big object. Okay, we call it the force of attraction, the field force. Okay, like gravitational force of attraction between sun and the earth, or between earth and the moon, that is acting at a distance. Similarly, this is the electric force. Okay, so this electric force is, a force, a field force. Okay, electric force, right? And similarly, this is a magnet, north and south pole of the magnet. This is iron, so iron will be attracted towards the magnet, or the north attracts the south pole of the other magnet. So these are the examples of the field forces. Now, Newton's first law of motion, we also call it the law of inertia. I will explain it later, inertia. What is the statement of this rule, the Newton's first law of motion? It says that if the net force means resultant force, the total vector force, when different forces are acting on an object. For example, this is an object of mass m. Force F1 is acting 5 Newton. Other force is acting F2, for example, 6 Newton. Okay, this is along the positive x direction, and this side negative x direction. Now, if you have another force, third force, I say let F3 is equal to 11 Newton. Now you see, if you add some of the forces, you see 5 plus 6 plus, these are the plus forces along positive x-axis, right? And the negative axis forces is minus 11. What is the answer? 0. So when you have the net force or the resultant force is equal to 0, the particle or the object's velocity cannot change. Of course, once the force is 0 on an object, you cannot change its velocity. And once velocity is the same initial and final, means you have acceleration 0. So we have here that if you have sum of the forces equals 0, acceleration is 0. You know, sometimes you have the forces acting on all the forces are acting along the x-axis, like this example I gave it to you. Sometimes, you know, the forces are acting along the y-axis. For example, I say, okay, you have this object, you have this force F1, for example, 2 Newton. Here you have 1 Newton and half Newton. Okay, another force half Newton. If you add them, you get the 0 answer, because this is 2 Newton, this is half plus half, 1 plus 1, 2. So 2 along the negative y-axis and 2 along the positive y-axis. So 2 minus 2 equals 0. But now this is along x-axis, so when you have net force resultant force 0 along x-axis, you have 0 acceleration along the x-axis. Similarly, you can have the y-axis forces if it is equal to 0, so y acceleration will be 0. Now, sometimes the forces are making some angle, so you have to find the x and y components. So you add all x components and then find all y components, but use these two rules. Now, what is inertia? You see, an object tends to, it wants to maintain, to keep the state of rest. If the object is at rest, it will try to be in the state of rest. It will resist, it will oppose any change to move it. Or that of the uniform motion. If it is moving, it will again resist, it will oppose to bring it at rest. This is called inertia. You might have seen that if your friend is running towards you, and if you want to stop him at one specific point, you apply the force, but still you cannot stop him exactly at the same point. He will still move a little bit in the forward direction due to inertia. Right? Now, similarly, if you have some object, some table, heavy object at rest, if you want to move it, initially it will resist, right? It will take some time to move. You have to apply more force. So the objects, they oppose, they resist any change in their state of rest or of motion. The mass of the object is a direct measure of the object's inertia. Means, for example, if you have this object and you have this object, this is number 1, this is number 2, this is M1, this is M2. You see, M2 is greater than M1. If you apply the same force, I say force is equal to 10 Newton on this small object and on this big object. It's easier to move this small object M1. Why? Because its mass is smaller. Mass smaller mean its inertia is smaller, right? And similarly, if you have greater mass, mean greater inertia. So inertia is direct measure of the object's inertia. Now, Newton's second law of motion. First we will discuss 3 laws, then we will discuss one example, and we will use our knowledge how to solve the problem. So Newton's second law of motion, you remember in the first law of motion, net force was 0, right? But here it's not zero, it's having some value. When you add, when you have one object and different forces are acting, you add all the forces and you don't have a zero resultant. So once you have any value not zero, then we have this rule: sum of the forces net, or the net force, is equal to the mass multiplied by the acceleration. So m is the mass of the object and a is its acceleration. So this is the rule. Again, as we discussed in the first law of motion, that when all forces are acting along x-axis, we can use sum of the forces along x-axis or the net force along x-axis. That was zero, but now you have mass multiplied by the acceleration but along the x direction. Similarly, if you have all the forces acting along y-axis, you add them and then that will be equal to the mass multiplied by the acceleration along the y-axis. Now, SI unit of force is Newton, right? Now you see force is equal to ma. So m, the mass, it is in kilogram, and a is the acceleration, which is meter per second square. So 1 kg meter per second square is equal to 1 Newton. So Newton is the unit of force. Right. Now, from this rule, we can write like this one: force divided by m is equal to a. I take this m in the denominator, right? So the acceleration, if you have, this is your, for example, I say you have force is equal to m. If you have small object, and what happens when you have the same force and you apply on some big object? You have small object and you have a big object, right? What happens when you apply the same force? You see, I'm using the same force. For example, I said 5 Newton on both object, this small object and this big one. So once you have the small object, it's easier to move it. So you will be having a big acceleration in this small object. But if you apply the same force here, 5 Newton, for example, here, 5 Newton here, in a big, if you have a big object with the greater mass, it's difficult to move it, so you'll be having small acceleration. So what does it mean? It means that acceleration is inversely proportional to the mass. So greater mass, smaller inertia. Smaller mass, greater acceleration, sorry. Okay? Right, smaller mass, greater acceleration. Greater mass, smaller acceleration. This is what I have used the size of the font to show you this basic idea. Right? Now, if, for example, you have one object which is, having this mass, I say, right? Okay, the mass is the same here, only one object, and if I apply small force here, right? So force is equal to ma. But if I apply the larger force on the same mass m, like this one, it's the greater force now, bigger force. So bigger force mean greater acceleration. So in this case, you see, force acceleration is directly proportional to the force. Means if you increase the force, acceleration will increase. If you decrease the force, acceleration will be decreasing. This is what I have used this font size here. Now, next you have Newton's third law of motion. You see, when two particles mean two objects, any two objects in physics, any object smaller or bigger, we call it particle, whether it is very small atomic level, table, chair, even a person, even heavy, I mean big objects like moon, earth and sun, we call them particle in the language of the physics. So when two objects or particles interact, the forces on them from each other have always same magnitude, but in opposite direction. You see, you have two objects. This is number one object and this is number two object. Now this object is applying a force on it, force on 1 by 2, F12, and this object applies a force on it, F21, force on 2 by the object number 1. You see what I have mentioned here, F12, the force on 1 due to 2 is equal to F21 force on 2 by first object, number 1 object. Magnitude is the same, but you see this negative sign? Negative sign shows that they are in the opposite direction. So same magnitude, both of the objects, they apply on each other the same magnitude force, but the direction of the force is opposite, right? We call it action-reaction pair. Once you are applying the force on one object, that is action, that object will apply the same amount of magnitude force on the other, but in the opposite direction. So that's why we call it action-reaction pair. Right. So F1 may be called the action force and F21 the reaction force, as I told you. Actually, either force can be action or the reaction. Of course, one, if you call one action, the other will be reaction. So action and reaction forces act on, of course, different objects. In this chapter, we'll be using, and if the physics people, I mean, they always draw the lines with the given information and they decide the direction and all these things because we are dealing them as vectors. So we call it the free body diagram. For example, I say, okay, you have one carton, its weight W, which is equal to the gravitational force or mg, it is acting vertically down along the negative y-axis, and reaction force of the earth in the opposite direction but the same magnitude, this is called the reaction or the normal reaction, we call it normal reaction. Okay, and this is the force. For example, you are connecting it with some rope or wire, piece of wire, and you are applying some force. This is force or T, tension. Tension means once you connect a wire with some weight, some mass, so it is under tension. Okay, so we call this force tension. So we have this side, for example, x-axis, and one side. This is the, first of all we decide the axis, plus y, minus y, plus x, minus x, and then we decide the forces accordingly. Now free body diagram again. So why I'm telling you, because you will be dealing with the different types of the forces. For example, you have this traffic light. So this is one wire at the roof, this is the string at the rope, and this is the third one. So all wires or the cables or the strings, they are under tension. So we give tension is the force, by the way, Like sometimes you have to prepare the lab reports, preparing for the quizzes and many other things, so you are under tension. But in physics language, whenever you connect some objects or the masses or the forces applying on some strings like these three, they are under tension. So you might have done one experiment, objects in equilibrium, okay, in the lab, right? So this is, for example, T in the first wire, T1, T2, T3. These are the angle they are making. This is just an example to show you. Now we draw the lines here. You see, T1, T2, and this T3, and all the angles. Here T3, and this is the gravitational force, right? So this is, it's in process. Right. Now you see, sometimes you might be looking at now you see, when you sometimes you see the forces like this one making some angle not on the horizontal surface. Okay, for example, sometimes you have an object, the mass m, it is on the horizontal surface. Simply the weight, which is the gravitational force, or what is the gravitational force? It's the weight or the force with which the earth attracts that object towards the center, vertically downward. So this is mg down, and the reaction is normal reaction n. So in this case, normal reaction n is equal to w, which is mg, when you are on the horizontal surface. Okay, but sometimes you are on the inclined plane like this one, where this is theta, right? Now this is, you see, weight is always acting vertically downward, right? This one. Now even if you are here on the inclined plane, this is vertically downward, this direction is your weight, mg, right? Now this is mg, and now we call them tilted axes, right? Because right now this is your positive x, this is your negative x, this is your positive y, and this is your negative y axis. But when you make them tilted axes like this one, like this one here, look here. So this is your direction positive x, this direction is negative x, this is positive y, and this is minus y. Okay, again, when you are on the horizontal surface, it's clear you might have been using for a long time plus x, plus y, and minus y. But when the object is making, when the inclined surface is making some, and when the plane is making some angle theta, so we call it inclined plane, and the object is here, then we say this is minus x, this is plus x, plus y, minus y, and we call them tilted axis, axis on the inclined plane. So this surface is called inclined because it is inclined, making some angle theta with the horizontal. Now you see, you might have seen that if this is any vector a, this is angle theta. You remember you did components of vector. This was ax is equal to a cosine theta. This was equal to a y component, a sine theta, right? Now keep in mind, I'm giving you the basic concept, and then you will be understanding how we have this mg sine theta and this side mg cosine theta. Otherwise, if I directly tell you, you will be confused. So keep in mind the basic idea. How? Look, focus on the theta. This is theta, sir. The side opposite to the theta in front of بالمقابل, okay, this is having sine component with it. Again, this is theta. The side in front of this theta is having a component with sine theta. So keep in mind. Of course, other one is cosine theta, and this is the vector a self. Instead of a, now we have mg. Okay, this vector going down is mg, gravitational force or weight of the object, this one. Now, when this is theta, you can do the geometric concept that this will be also theta. This angle is theta. And we have to keep in mind the rule for adding two vectors, right? Again, I make it here for you, for example, right? Okay, so if this is mg, okay, this is theta, and this vector and this vector. Okay, so this vector is coming here and this should go like this one. You see, again, the basic concept I gave you, this is theta. In front of theta you have side, this side having sine theta involved in. So okay, so this is again theta. In front of it, it should be, I write it here for it, so this is mg sine theta, right? Sine component, so sine theta here in front of theta, this one, make it clear. All right, so this is mg itself, this one, this is mg sine theta, and this one is mg cosine theta. Again, this mg sine theta is parallel to this vector, okay, this one. So this is mg sine theta again, and this one is mg cosine theta. This is the force of friction, okay, frictional force opposite in the direction of opposite to the direction of motion, and this is mg sine theta. So you will be dealing with these concepts. Please keep in mind. All right. Now, next we are going to use, this example. We'll be solving it. Please look how we'll be doing it. First of all, try to understand the physics in this problem. A sled is tied to a tree on a frictionless snow-covered hill, as shown in the figure. The sled weighs 77. So weight mg, which is equal to 77 Newton. Newton is the unit of force or unit of weight. Okay, so W is equal to directly given, mg is directly given to you. Find the magnitude of the tension force. So you have to find out tension in the string or the rope and the normal force. Okay, so you have to find these two forces using what we already done with the Newton's first, second and third laws. All right, so how we'll be doing it, you see, first of all, look, this is the rope, so there is a tension in it in this direction, and we decide that this is the plus x-axis, as I told you, tilted axis. This side is minus x-axis. Okay, this is plus y, and this is minus y axis. Now, once decided the tilted axis or the axis on the inclined plane, because this is making an angle theta, you see this theta which is 30 degree, so this is again theta which is 30 degree, this one, okay, this angle. Now one thing is clear, that this is mg itself, right, always down, weight is always down, mg, you cannot say this direction and this direction, understood, always down. Now this is theta, so this will be like this one, this direction, okay, this direction, which is the side in front of theta is always mg sine theta. Let me write it here. So this is mg sine theta. The basic concept I just finished last topic. This is theta in front of the side in front of theta having the sine component. So this is mg sine theta. This is mg and this one is mg sine theta. If I take the parallel here, so this is your mg sine theta along negative x-axis. Alright, now, and this is the normal force opposite to this, perpendicular to this. So this is mg, this side is mg cosine theta, okay, again this is mg sine theta, parallel here I put it, and this one is mg cosine theta. Now what we do to find out these two, we use this rule. The force is, keep in mind that whenever by the way, when you have all forces acting along x-axis, you add them like vectors and you will get the resultant. Similarly with y-axis. But when even one force is making some angle, like in this case, keep in mind you have to go for x component, add all x component, right, and find out the magnitude, and similarly add all y components separately. So we are applying separately the sum of the forces, since it is not moving at rest, so this is the Newton's first law of motion equals 0. Sum of the forces equals 0. Alright, now first of all you have to decide the forces along x-axis. Along positive x-axis, this force positive, this is tension here, tension in the rope, okay, so tension this side, and this side you have, you know, which force, this force mg sine theta. Any other force along x positive or x negative? No. Let me close this box. This box is just for your better understanding. Now the positive force, I take positive, okay, this is positive and this is negative. So positive force T minus mg sine theta is equal to 0. Alright, now I take this to the other side, it will become positive. T is equal to mg sine theta, right, mg sine theta. Keep in mind, if mass is given in kg, kilogram, you multiply with 9.8 g, gravity, expression due to gravity. But now why I'm putting this bracket, because the weight is given directly, no need to multiply again with 9.8, it's given directly here. Okay, so 77 sine theta. So you get tension T, this is sine 30 rather, sine 30 degree, sine 30 degree. So you would get 38.5 Newton. So this is your tension. Okay, finish. Now we need to find out the normal reaction. So sum of the forces along y-axis equal to 0. Let me decide the forces along y-axis. Okay, y-axis forces, y-axis positive and y-axis negative. Now y-axis positive, you have this force, y-axis positive, normal force. Okay, this is n normal, and the opposite negative y-axis, you have force, this force mg cosine theta. So mg cosine theta negative. So positive force, negative force, right, minus mg cosine theta is equal to 0. I take this to the other side, it will become positive mg cosine theta, mg 77 cosine 30, you would get 66.7 Newton. Okay, this is your normal reaction. So that's it. Right? Now, then we go to the next question. The combined weight of the crate and the dolly. You have this crate, for example, right, and you put it on some dolly here. Okay, so combined weight is, dolly in the crate is this much. Okay, so this is your W, which is equal to mg, this much, 3 times 10⁻²⁴ Newton. If the man pulls the rope with a constant force of, this is your force. What is the acceleration? So you have to find out the acceleration of the system crate plus the dolly, and how far will it go, and you have to find out delta x, how far will it travel. Assume the system starts from rest, mean initial velocity is equal to 0. So first of all, we find out acceleration. You see, we have right. So first of all, we have to find out, sum of the forces acting on the object is equal to ma. Since the motion is along the x-axis, so allow me to write this one here. Right, now we have A is equal to sum of the forces along x-axis over m. From this equation you will get. Okay, now how much is the force? Only force is F, which is given to you. How much? 20 Newton over mass. Mass is not given to you, but weight is given to you. Weight is given to you, mg. All right. So it implies m is equal to w over g. So w is equal to how much given? Yes, this is w. 3 times 10 raised to 2. 2 divided by 9.8. You get the mass 30.6 kg. You use this mass over here and 30.6, you would get acceleration meter per second square. It will be 0.654. Right now, the second part, which is the displacement, how far will it go? We have VIT plus half a, since we're talking about the acceleration about x-axis, AT square. Right now, time is given to you 2 seconds in the question. Right, it starts from rest. This is 0, so half a, you just finish, t 2 seconds, so you get delta x 1.31. okay, take 1 minute. I think this is the end of the first lecture of for chapter 4. We will continue in the next lecture.